In the beginning, there was a silence so profound that even the word nothing feels too heavy, too pregnant with implication to capture its essence. The universe as we know it, its stars and galaxies, the tapestry of space and time, emerged from this silence in an instant of unimaginable heat and density. The Big Bang, as the physicists call it, marks the dawn of time and space, the luminous birth cry from which all things have sprung. Yet as our minds press against the boundary of that primal moment, a deeper question lingers with an ache almost ancient. What, if anything, came before it? Was there truly a nothingness, a vast blank, or does the universe carry within its fabric the echoes of a more ancient story? To begin unspooling this greatest of mysteries, we must first walk the perimeter of what is known. The Big Bang, far from being a conventional explosion, was the rapid expansion of space itself. About 13.8 billion years ago, all that would become the observable universe was compressed into a singularity, a point of infinite density and temperature. In the fractions of a second that followed, those earliest moments known as the Planck epoch, the laws of physics as we know them break down. General relativity, Einstein's magisterial theory of gravity, collides with quantum mechanics, the language of the subatomic world, and the resulting mathematics dissolves into paradox and uncertainty. Within this fog of unknowing, physicists have found themselves compelled to imagine, to theorize, to reach for a language that transcends the limits of experiment and observation. The first of these imaginings is as stark as it is unsettling. Perhaps there was nothing before the Big Bang because time itself was born with it. Stephen Hawking, the physicist whose mind roamed the farthest reaches of cosmology, once likened the question of before the Big Bang to asking what is north of the North Pole. In this conception, time is not a river flowing endlessly backward. It is a dimension that, like the surface of a sphere, has no edge, no boundary, no before. The equations of general relativity, when extended backward, suggest a moment where time and space curve together into a smooth, finite, yet unbounded whole. A beginning that is not a beginning in the conventional sense. But even this elegant idea harbors a restlessness, a sense that something more might lurk beyond the horizon of the knowable. For centuries, humanity has been haunted by the idea of cycles, of endless return. Ancient Indian cosmologies, for instance, spoke of the universe as passing through infinite cycles of creation and destruction, each eon following the last in a cosmic rhythm without beginning or end. In the 20th and 21st centuries, this mythic intuition found new mathematical clothing in the cyclic universe models. Among these, the Ekpyrotic scenario stands out, a theory born from the mathematics of string theory and from the minds of Paul Steinhardt, Neil Turok, and their collaborators. In the Ekpyrotic model, our universe is but one of two immense, three-dimensional brains floating in a higher dimensional space. Periodically, these brains collide, unleashing a storm of energy that triggers a new Big Bang. Each collision wipes away the memory of the previous universe, resetting the cosmic stage for another cycle of creation, expansion, and eventual contraction. The scars of ancient collisions, it is theorized, might linger as subtle imprints in the cosmic microwave background, the faint afterglow of the last Big Bang. Yet, despite its mathematical beauty, the Ekpyrotic scenario remains perched on the edge of speculation. The higher dimensions it invokes are invisible to experiment, their existence inferred only through the delicate dance of equations. Other cyclic models dispense with brains and extra dimensions, imagining instead that the universe expands and contracts in an endless series of Big Bangs and Big Crunches. The Russian physicist Alexander Friedmann, in the 1920s, was among the first to glimpse this possibility in the equations of general relativity. Decades later, the idea would be revived, challenged, and refined as new data poured in. Yet with the discovery that the expansion of the universe is accelerating, driven by the mysterious force known as dark energy, the prospect of a future Big Crunch appears ever more remote. Instead, the universe seems destined for a cold, eternal dispersal, its galaxies drifting ever farther apart. Still, the yearning for cycles persists, finding new expression in the mathematics of quantum gravity. In loop quantum cosmology, a theory pioneered by Martin Borjewald and Abhay Ashtekar, space-time itself is granular, woven from tiny loops of quantum geometry. Here, The Big Bang is not a singularity but a bounce, a moment when a contracting universe, compressed to the smallest possible volume, rebounds and expands anew. In this view, the universe before the Big Bang may have been a vast cosmos collapsing under its own weight, only to be reborn in a luminous surge of expansion. The mathematics of this bounce, though beautiful, is still being tested against the faint signals of the early universe, the patterns of polarization in the cosmic microwave background, the distribution of primordial gravitational waves. Beyond cycles and bounces, another vision shimmers on the horizon, the multiverse. This idea, both exhilarating and unsettling, suggests that our universe is but one bubble in a vast frothing sea of universes, each with its own laws, its own physics, its own beginning and end. In the inflationary multiverse, a theory developed by Alan Guth, Andre Linde, and others, the universe underwent a brief but stupendous burst of exponential expansion, a process known as cosmic inflation. In some versions of this theory, inflation never truly ends. It continues eternally in distant regions of space, spawning an infinite ensemble of pocket universes. Our Big Bang, then, is merely the local chapter in a much grander story, a single firework in an endless cosmic display. The mathematics of eternal inflation is compelling, its equations humming with possibility. Yet the multiverse is a theory perched on the knife edge between science and philosophy. Its other universes, by definition, cannot be observed, their light forever beyond our reach. Some physicists, like Sean Carroll and Max Tegmark, embrace the multiverse as a logical consequence of inflationary theory and quantum mechanics. Others, like Paul Steinhardt, worry that it renders the very notion of scientific prediction meaningless, replacing explanation with a dizzying lottery of possibilities. There are other, stranger visions still, each a testament to the restless creativity of the scientific mind. Roger Penrose, the Nobel laureate mathematician, has proposed a model he calls conformal cyclic cosmology. In this view, the universe expands forever, its contents diluting until all that remains are massless particles, moving at the speed of light. At this point, time and space lose their meaning, and the universe becomes conformally identical to the state it had at its birth. A new Big Bang emerges from the ashes of the old, and the cycle begins again. Penrose has even claimed to find faint evidence for this theory in the patterns of radiation left over from the last Big Bang. Enigmatic circles in the cosmic microwave background, perhaps the ghostly imprints of ancient black holes evaporating in a previous aeon. As we move further from the shore of the known, the speculations become more audacious. Some theorists, inspired by the mathematics of quantum mechanics, suggest that the universe could have tunneled into existence from nothing, a quantum fluctuation in a primordial void. In this view, advanced by Alexander Vilenkin and others, nothing is not the absence of all things, but a state of zero classical space and time, seething with potentiality. The universe, they argue, is the ultimate free lunch, its positive energy balanced by an equal and opposite gravitational energy, allowing it to spring into being without violating the laws of physics. Yet, even this vision strains the limits of language and comprehension. What does it mean for something to exist before time itself? Can mathematics alone conjure a world from nothingness? The quantum vacuum is an abstract entity, a mathematical object more than a physical reality. It is here, perhaps, that science begins to shade into philosophy, that the boundaries of the empirical blur into the realm of metaphysical speculation. The debate is not merely academic. It cuts to the heart of what science can and cannot explain. The scientific method, for all its power, is rooted in observation and experiment. The Big Bang itself leaves behind a wealth of evidence: cosmic microwave background radiation, the abundance of light elements, the large-scale structure of galaxies that allows us to reconstruct the history of the cosmos back to the first fractions of a second. But before that point, the evidence grows thin, the signals faint, the mathematics speculative. Each theory of the pre-Big Bang era is a tapestry woven from the threads of inference, analogy, and hope. And yet, the quest continues. In laboratories around the world, scientists labor to probe the earliest moments of the universe, smashing particles together at energies that approach the conditions of the Big Bang. The Large Hadron Collider at CERN, a ring of supercooled magnets buried beneath the French and Swiss countryside, has revealed the Higgs boson, the last missing piece of the standard model of particle physics. Yet it has also exposed the profound limitations of our knowledge. The standard model for all its successes cannot explain why the universe contains more matter than antimatter, nor the true nature of dark matter and dark energy. It is silent on the question of what, if anything, came before the Big Bang. In the deserts of Chile, the Atacama Cosmology Telescope and the Simons Observatory scan the sky, searching for the faintest ripples in the fabric of space-time, primordial gravitational waves perhaps, or subtle anomalies in the cosmic microwave background. Each data point, each pattern, is a clue in the great puzzle of origins. The hope is that someday a telltale signature will emerge, a fingerprint of a previous universe, a scar left by a bouncing cosmos, a hint of higher dimensions. Consider for a moment the BICEP 2 experiment, which in 2014 announced the possible detection of primordial gravitational waves, ripples in space-time generated by cosmic inflation. The result, later found to be contaminated by galactic dust, was a sobering reminder of the difficulty of peering back to the universe's earliest moments. Yet, it also illuminated the path forward. Only by pushing the boundaries of observation can we hope to distinguish science from speculation, history from myth. Amid these technical quests, the question of origins continues to inspire philosophical reflection. What does it mean for time to have a beginning? If space and time are emergent properties of a deeper, pre-physical reality, as some versions of string theory or quantum gravity suggest, then the very notion of before the Big Bang may be as meaningless as asking what lies south of the South Pole. Yet the human mind recoils from such boundaries, yearning always to peer beyond the veil. It is here that language falters, that poetry begins where mathematics ends. The ancient Greeks spoke of chaos, the yawning chasm from which all things emerge. In the book of Genesis, creation is a word spoken into darkness, a command that brings order from the void. In the mathematics of modern cosmology, the void is alive with possibility, a seething froth of quantum fields and virtual particles. The boundary between existence and non-existence is blurred, smeared out by the uncertainty principle, rendered ambiguous by the mathematics of Hilbert space and Feynman path integrals. Even as we press against these boundaries, the universe offers reminders of its strangeness, its unwillingness to be captured by human expectation. The cosmic microwave background, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, reveals a universe that is astonishingly uniform, yet marbled with tiny fluctuations. These ripples, mere 1 part in 100,000, are the seeds from which all structure has grown. But why is the universe so smooth on large scales? Why is it so flat, so finely balanced between eternal expansion and eventual collapse? Inflationary theory provides one answer: smoothing and flattening the cosmos in a fraction of a second after the Big Bang. But the deeper question, why this universe with these laws and not another, remains open. The anthropic principle, controversial and divisive, enters here. It suggests that we observe this particular universe because only in such a universe can observers like ourselves exist. In the vast multiverse, most universes are sterile, lifeless, ruled by physical constants inimical to the emergence of complexity. Ours is special not because of any deeper necessity, but because it is one of the rare cosmic lottery tickets that permits the rise of stars, planets, and minds. For some, this is a satisfying answer, a way to make peace with the apparent arbitrariness of the cosmos. For others, it is a retreat from explanation, a surrender to the inscrutable. The debate is ongoing, fierce, and unresolved. It is a reminder that science, for all its power, is a human enterprise, driven by curiosity, shaped by culture, bounded by the tools and concepts at our disposal. The quest to peer before the Big Bang is, in the end, a mirror of our deepest longings. It is a search not only for the origins of matter and energy, but for meaning, for purpose, for a place in the vast unfolding story of the cosmos. Each theory, cyclic universes, multiverses, quantum bounces, creation from nothing, reflects a different facet of our desire to find order in the void, to glimpse the infinite in the finite. As we journey through these theories, let us pause to consider some of the figures who have shaped this quest. Georges Lemaitre, the Belgian priest and physicist, first proposed the idea of a primeval atom, the forerunner of the modern Big Bang, drawing together the insights of Einstein's relativity and the expanding universe discovered by Edwin Hubble. Lemaitre's vision was both scientific and theological, a synthesis of reason and wonder. Later, George Gamow, Ralph Alpher, and Robert Herman predicted the existence of the cosmic microwave background, a relic radiation that would, decades later, be detected by Arno Penzias and Robert Wilson, forever changing our understanding of the universe's origins. Each discovery, each advance has been both an answer and a provocation, opening new vistas even as it raises new questions. The detection of the Higgs boson in 2012 confirmed the mechanism by which particles acquire mass, yet left unexplained the nature of dark matter and dark energy. The observation of gravitational waves by LIGO and Virgo has opened a new window on the cosmos, allowing us to hear the echoes of colliding black holes and neutron stars. Yet, the primordial gravitational waves that would reveal the secrets of cosmic inflation remain elusive, their signal buried in the noise. Consider the cosmic neutrino background, a faint sea of nearly undetectable particles, relics from the first second of the universe's existence. Detecting these ghostly messengers would offer a glimpse further back in time than any photon, perhaps even to the moment of baryogenesis when matter overcame antimatter to shape the world we know. The search for such signals is ongoing, the detectors ever more sensitive, the hope ever more fervent. In the halls of theoretical physics, the debate continues. String theory, with its vibrating filaments and extra dimensions, offers one vision of the pre-Big Bang cosmos. In some versions, the universe is a 10 or 11-dimensional membrane, its visible dimensions curled up into tiny, invisible loops. Collisions between branes, as in the Ekpyrotic scenario, could trigger new universes, each with its own laws and constants. The mathematics is intricate, the predictions subtle, the experimental evidence elusive. Elsewhere, the holographic principle, born from the study of black hole entropy by Jacob Bekenstein and Stephen Hawking, suggests that the universe is a projection, a three-dimensional image encoded on a distant two-dimensional boundary. In this view, the information content of the universe is finite, bounded by the area of its horizon. Some theorists, like Juan Maldacena, have explored the idea that our universe is a hologram, its deepest structure encoded in the mathematics of conformal field theory. What this means for the question of before the Big Bang is still unclear, but it hints at a reality more strange and subtle than we can yet imagine. From the mathematics of quantum gravity emerges another possibility, that time itself is an emergent phenomenon, a property that arises only in the macroscopic world. In the timeless equations of the Wheeler-DeWitt equation, named for John Wheeler and Bryce DeWitt, time disappears, replaced by a static wave function of the universe. In this view, the universe is a block, an unchanging whole, in which past, present, and future coexist. The flow of time is an illusion, a trick of perspective. What then does it mean to ask what came before the Big Bang, in a reality where before and after have no meaning? These are questions as much philosophical as scientific. They remind us that the boundary between knowledge and speculation is always shifting, always porous. Theories of the pre-Big Bang cosmos are tested not only by their mathematical consistency, but by their ability to make contact with observation, to predict new phenomena, to explain the world we see. Yet, as the history of science shows, today's speculation may be tomorrow's fact. The idea of an expanding universe was once dismissed as fantasy. The existence of black holes, gravitational waves, and cosmic inflation, once speculative, are now pillars of our understanding. Still, some questions may be forever beyond our reach. The limits of observation, the boundaries of what can be measured or inferred, may render the pre-Big Bang era permanently mysterious. This is not a failure, but a testament to the richness of the universe and the humility of our quest. As the astronomer Carl Sagan once wrote, "We are a way for the cosmos to know itself." Our curiosity, our longing to understand, is itself a product of the universe's unfolding, a ripple in the great sea of being. Let us return, then, to the present, to the world of stars and galaxies, of atoms and life. The universe, for all its strangeness, is also our home, the stage on which the drama of existence unfolds. Its history is written in the light of distant galaxies, in the radio whispers of the cosmic background, in the patterns of atoms and molecules. Each discovery, Each theory is a step on the long journey from ignorance to understanding. The search for what came before the Big Bang is not merely a scientific quest, but a human one. It is driven by the same impulse that led our ancestors to gaze at the stars, to tell stories of creation and destruction, to seek meaning in the vastness. Whether we find definitive answers or only ever more beautiful questions, the journey itself is a testament to the power and mystery of the cosmos. In the end, perhaps, the universe is not a puzzle to be solved, but a story to be lived. A story whose opening chapter is still being written, whose ending lies forever beyond the horizon. The theories we have explored, cyclic universes, multiverses, quantum bounces, creation from nothing, are not final answers, but invitations to wonder, to imagine, to dream. They are reminders that the universe is stranger, deeper, and more beautiful than we can yet know. As we gaze into the darkness before the dawn, let us remember that every answer opens new questions, that every discovery is a door to new mysteries. The boundary between science and speculation is not a wall, but a bridge, a path that leads us ever onward, ever deeper, into the heart of creation. The silence before the Big Bang is not empty, but alive with possibility, a canvas on which the universe paints its story, one moment, one theory, one question at a time. The journey to understand what, if anything, existed before the Big Bang is not one that can be completed in an evening, or a lifetime, or even in the sum of all human endeavor. It is a journey without end, an endless spiral into the mysteries of time, space, and existence itself. Consider how the very fabric of space-time, as described by Einstein's field equations, behaves near the singularity. General relativity, our grandest theory of gravity, becomes silent at the Planck scale. Distances of about 10 or 35 meters and times of about 10 or 43 seconds. Here, quantum fluctuations are so violent that the smooth continuum of space-time breaks down, replaced by a seething foam of probabilities and uncertainties. The Planck epoch marks the edge of our theoretical map, the boundary beyond which our current laws of physics cannot venture. To move beyond this boundary, physicists seek a theory of quantum gravity, a framework that will unite the smooth geometry of general relativity with the granular, probabilistic world of quantum mechanics. String theory is one such candidate, positing that the fundamental constituents of reality are not point particles, but tiny vibrating strings, their various modes of vibration giving rise to the zoo of elementary particles. In string theory, the universe may have more than the familiar 3 dimensions of space and 1 of time, perhaps as many as 10 or 11, most of them curled up into compact manifolds too small to detect. Within this mathematical universe, new possibilities emerge. The Ekpyrotic scenario, as we have seen, imagines our universe as a 3-dimensional brain, floating in a higher dimensional bulk. Collisions between brains can trigger events akin to the Big Bang, each collision birthing a new universe, each cycle erasing the memory of the last. The mathematics of brain cosmology is intricate, involving the geometry of Calabi-Yau manifolds, the dynamics of moduli fields, and the physics of extra dimensions. Yet for all its beauty, it remains a theory in search of experimental support, a hypothesis awaiting the verdict of observation. Loop quantum gravity, another contender for a theory of everything, dispenses with strings and brains, focusing instead on the quantum geometry of space-time itself. In this framework, space is composed of discrete, finite loops, woven together into a spin network. At the Planck scale, these loops form a granular structure, with area and volume quantized in units of the Planck length and volume. In loop quantum cosmology, the Big Bang is replaced by a big bounce, a transition from a contracting universe to an expanding one. The equations describing this bounce are derived from the quantum properties of space-time and suggest that the universe before the Big Bang was not a void, but a cosmos collapsing under its own gravity, poised on the knife edge of rebirth. The implications of a cyclical or bouncing universe are profound. If time has no beginning, if the universe has always existed in some form, then the question of ultimate origin is transformed. Instead of asking what caused the universe to exist, we are invited to explore the dynamics of eternal return, the endless dance of expansion and contraction, creation and destruction. This vision resonates with ancient philosophies, from the Hindu concept of the yuga cycles to the Stoic doctrine of eternal recurrence. Yet the evidence for such cycles is elusive. The cosmic microwave background, our oldest light, is a snapshot of the universe 380,000 years after the Big Bang, its patterns encoding the physics of the early cosmos. Tiny anomalies in this background, cold spots, alignments, unexpected symmetries, have been the subject of intense scrutiny, with some claiming to find evidence for previous cycles, others dismissing these findings as statistical flukes. The Planck satellite, launched by the European Space Agency in 2009, has mapped the microwave background with unprecedented precision, revealing a universe that is, on the largest scales, remarkably uniform and isotropic. The anomalies, if they exist, are subtle, their interpretation fraught with uncertainty. The multiverse, perhaps the boldest of all theories, offers a different kind of infinity. In the inflationary multiverse, our universe is merely one bubble in an endless froth of creation, each bubble expanding into its own space-time, each with its own laws and constants. The process of eternal inflation, first proposed by Alan Guth and further developed by André Linde, suggests that quantum fluctuations in the inflaton field, a hypothetical scalar field responsible for cosmic inflation, can cause different regions of space to inflate at different rates, spawning an infinite hierarchy of universes. The mathematics of eternal inflation is elegant, its implications staggering. Our observable universe is but a tiny island in a vast, unobservable sea. The constants of nature, such as the strength of gravity, the charge of the electron, the cosmological constant, may vary from one universe to another, creating a cosmic landscape of possibilities. The anthropic principle, controversial though it may be, finds a natural home here. We observe this universe because it is one of the few that permit the existence of observers. Yet the multiverse poses deep challenges to the philosophy of science. If other universes are fundamentally unobservable, if their existence can never be tested or falsified, then in what sense are they real? Some physicists argue that the multiverse is a logical consequence of well-established theories, and that its predictions, such as the value of the cosmological constant, can be probabilistically tested. Others, like George Ellis and Paul Steinhardt, caution that the multiverse risks undermining the very basis of scientific reasoning, reducing explanation to a matter of chance. The debate is ongoing and unlikely to be resolved soon. It is a reminder that the boundaries of science are not fixed, but evolve with our understanding, our tools, and our imagination. Beyond the multiverse, even stranger possibilities beckon. The concept of creation from nothing, championed by Alexander Vilenkin, Edward Tryon, and others, suggests that the universe is a quantum fluctuation in a primordial void. In this view, the laws of quantum mechanics permit the spontaneous creation of universes, provided that the total energy is zero. The positive energy of matter is exactly balanced by the negative energy of gravity, allowing the universe to spring into being without violating conservation laws. The mathematics of quantum cosmology is subtle, involving the Wheeler-DeWitt equation, the Hartle-Hawking no-boundary proposal, and the path integral formulation of quantum mechanics. In the Hartle-Hawking model, proposed by James Hartley and Stephen Hawking in 1983, the universe has no boundary in time, no sharp beginning, no edge, but a smooth, rounded geometry akin to the surface of a sphere. Time, in this model, is a dimension that emerges from the geometry of space, losing its classical meaning near the origin. The philosophical implications of these models are profound. If time itself is an emergent property, if the universe has no beginning in the conventional sense, then the question of before the Big Bang may be meaningless. Yet the human mind recoils from such boundaries, yearning always to peer beyond the veil. In the end, the quest to understand what came before the Big Bang is as much a journey of the imagination as of the intellect. It is a journey that has taken us from the ancient myths of creation to the cutting edge of theoretical physics, from the poetry of Genesis to the mathematics of quantum gravity. Each theory, each model is a window into the mystery of existence, a glimpse of the infinite, shimmering just beyond the horizon of the known. As we stand at the edge of this mystery, it is worth remembering that the universe, for all its strangeness, is also our home. Its history is written in the light of distant galaxies, in the radio whispers of the cosmic background, in the patterns of atoms and molecules. Each discovery, each theory is a step on the long journey from ignorance to understanding, a journey that perhaps will never end. The silence before the Big Bang is not empty, but alive with possibility, a canvas on which the universe paints its story, one moment, one theory, one question at a time. As the night sky arcs overhead, as the galaxies wheel in their ancient dance, the question remains, what if anything came before the beginning? Perhaps we will never know. Perhaps the answer lies forever beyond the reach of observation, forever hidden in the darkness before the dawn. Yet it is in the asking, in the longing, in the restless curiosity of the human spirit, that the universe finds its voice. The search for origins is not a puzzle to be solved, but a story to be lived. A story whose ending is, always, a new beginning. In the silence before the Big Bang, in the darkness before the dawn, the universe waits, and we wait with it, listening for the first faint whisper of creation,